Okay, let's take a look at a little more complicated projectile problem. Let's say someone's going to do a long jump, and they leave the ground at an angle of 20 degrees, and they have a displacement for their long jump, or a total jump of 8.9 meters. That's, I think, pretty close to the Olympic record. Uh, that's not a lot of information, so this problem ends up being a little bit trickier. So if we think about taking a look and drawing a picture at the problem, we're going to leave the ground, right, at an angle with an initial velocity, and we'll follow the parabolic trajectory, landing over here. And one thing about these kind of problems that might be useful to do for some of them is another piece of information that we know that we're not always given in the problem, in the paragraph, is that the velocity at the very top, Vy, is equal to 0. That allows us to break a problem like this in half. We know that that happens at half the time and half the distance that we would travel. Let's see how that can become useful in doing some problem solving. So we'll use our two equations, one for y, the velocity in the y direction. That's going to allow us to take advantage of this 0 value here. And then, of course, the other equation we'll use is the one with the delta x, so we have that information. But if you take a look, we end up with two equations and two unknowns. So we have a little bit of work to do. All right. So if we use that Vy equals 0, or the y velocity becomes 0 at that tangent point right at half the time, we can plug that in. But what we just have to keep track of is realizing that this means for half the time, because that's the boundary we're putting on it, is 0. So that gives us our equation, and we don't know the time, but we can solve for that symbolically here and realize that we don't know this initial velocity either. But we still have another equation we can use right here. So if we get rid of time out of these equations, we can now use the delta x equation. We modify it a little bit, okay, because we solved for half the time here. We know that we would be at half of our range, or half of our distance in the x direction. So just to keep track of that, I'm putting that little subscript of a half on there. And we can now take this value that we found, t1/2 right here, substitute that in to get rid of that unknown time, and the only variable we're left with that we don't know is the one we're looking for, which would be the initial velocity we're going to jump with. So taking this value and substituting it in here gives us this expression, and then working that down, all right, just doing a little bit of algebra, and then finally solving that expression for the initial velocity squared. All we need to do then is take the square root of both sides, and then we have to make sure we're putting in the right numbers, okay? Because if you take a look in here, we know g, and we know the angle of launch, 20 degrees, but we don't know, we have to make sure that we put in half the distance of the jump, not that whole distance. So remember, the jump's whole distance was 8.9 meters. So when I plug it in the formula here, what I'm going to have is 9.8, and I'm going to take half of that total distance value, place that in there, and when I calculate it out, I end up with an answer of 11.6 meters per second. That is fast.